There is no obvious physical meaning to drawing vectors for displacement that happen one after the other from the same point. Similarly, it looks strange to draw one velocity vector and then another straight after it. All the same, this is exactly what can be done. Any two vectors can be added in their representation by either approach, and the equivalence of the two on paper can be shown again and again. Accelerated motion, whether showing itself in speeding up, slowing down, or changing direction, is a direct result of one or more forces acting on an object. Those forces together and their vector addition would show the single force that could take the place of all those forces in causing the identical accelerated motion. This single force is called the resultant. By the end of the lesson, the learners should be able to see and use different ways of working with vectors, describe and explain the relationships between force and acceleration on change of momentum, and read, analyze, and solve problems using meaningful techniques.
Look at what we have done here.
Mr. Mtimkulu will provide the learners in his class with two examples of vector addition, one involving two displacements following each other, and one involving two velocities affecting the same object.
We want the resultant of these two vectors. So these vectors have been drawn head to tail, okay? They are following each other, okay? When you come here at the end, then you have got to take your protractor, then you measure your direction again. Your direction must be measured from north, okay, which is this one. That's your resultant, okay? And if you look at this figure, what type of diagram does it form? Triangle of vectors, okay? That is this method of finding vectors. There are two of them, of course, will form a triangle of vectors, okay? There are two of them, then there is a resultant, and they form a triangle of vectors, okay? So that's one way of finding a resultant. Also, I also have with me here another example which I will also try and explain to you. An object was moving, or an aeroplane was flying at a bearing of 180 degrees at the speed of 10 meters per second, for argument's sake, all right? Now here is a force that is blowing at 2 meters per second towards the east, which is the bearing of 90 degrees, okay? Now, will the plane still continue to go towards the south?
No.
No, it will change the direction, okay? It will change, it will move towards the east, okay?
Yes.
Right. And then how do you find the resultant of the two, okay? Right. The first method was the head to tail method, okay? Okay. Now, this one is different, okay? It is, you say you draw this one. We have drawn another vector, which is the same as that here, okay? And then you put another one like this. Unfortunately, I don't have that one long. You put it here, you draw another one here, okay? Where this point intersect, okay? Then you join these two lines, okay? And then you draw your resultant, okay? And then you can measure the angle that the resultant make, maybe with this angle, okay? Then, so you can then say you measure the resultant here and you find it to be what? Maybe to be, they say this is approximately 15 meters per second. Then you will say, my resultant is 15 meters per second at a bearing of what? 160 degrees. Do you get my point? Now, one thing that you must know is, if, for instance, I block this, I'll take paper and block this. What do you get there?
Triangle.
A triangle, is it? So a parallelogram is actually a set of two what? Two triangles, okay? So that's what you need to understand here. That's a triangle, and these two together they form what you call a parallelogram.
Mr. Mtimkulu has an interesting style of presentation. Not everybody can work that way, and nor should everybody try to. But it is important for a teacher to be able to act out, present, and show people things clearly and interestingly. And this he does. And this is important.
Then I will go on and maybe give you some examples to do very quickly, and then I would like to get your input as soon as possible. Use also the parallelogram method.
The learners now have to do 2 exercises, finding the resultant of 2 vectors using both methods of vector addition.
And what is the most correct one? I know you've done it.
I got 113 meters on a bearing of 26.6 degrees.
The educator now works through the learners' answers, correcting them where necessary.
Now, okay, she's coming up with something different now. Hey, why is it so different? Okay, yes?
112 meters. It's a bearing of 15 degrees.
So what we're going to do here is, right, I've done the same thing here. That is the first force I've represented here, which is 80 newtons at 90 degrees, which is east. Then the second part is this one now. Now I've tried to make a parallelogram of vectors like I showed you earlier on, right? I've drawn what is known as a parallelogram. It's important for learners to understand the relationship that exists between their everyday life experiences with some scientific concepts. And the only way by which that can be inculcated among learners is to try and investigate the applications of science into everyday life experiences, okay? Like if you talk about momentum, they should understand that momentum can be related to some of the sports in which they participate. Okay. You must try to catch it at about within the same time, okay? Just throw it slowly, and the second thing you'll try and throw it faster. Let's hope you'll be able to catch it, okay? You know how to catch, eh? Okay, fine, catch there. Okay, right? No, faster now? No, yes? Okay, fine, thank you, thank you. Right, okay, you are going to tell us what you have observed, okay? What can you say? What observed?
According to the forces, I think time is shorter.
Now remember, when you stop something, you have to apply a force which acts in the opposite direction to that of motion. Otherwise it won't stop, all right? Like when you stop a car, you have got to apply brakes. And by applying brakes, you are applying a frictional force which acts in the opposite direction. So even when I throw something at you and you stop it, you have to apply a force which acts in the opposite direction.
I think force, it must be less because a cricket ball is a light ball.
They were both moving at the same speed, okay? So their velocities were the same, okay? But now, in the same case, I said you throw it faster, okay? And you try and catch it, the same type of ball. Now it's faster.
I think when you increase the speed,
the educator leads the learner to a better understanding of his observations.
More reaction force.
For the same ball, same type of ball, with the same mass, but different velocities. So what you can conclude? What can you conclude about stopping a ball now?
You need more force.
You need more force, okay? Remember, force is the rate of change of momentum. We looked at another example whereby we use now different balls. We use balls, different types of balls. This one is very light, this one is too heavy, okay? It can only be held comfortably by people who are muscular like me, all right? Now, okay. Now we saw when we tried to stop here. I had my friend here who tried to stop this ball. Where is he? He can explain to me what happened.
It's heavier than the tennis ball.
It's heavier than the tennis ball. That's one thing that I'm getting from you. Anyone else who wants to have some input? Please, people, let's have your input.
A shot put ball need more force to stop it.
Yes.
And the tennis
because
ball,
it has got what? Because why?
More, it has more mass.
So now we are just going to apply this concept of momentum. It says Macayan bowled cricket ball of mass 0.16 kg at a velocity of 40 meters per second. This hits a batsman on his thigh. You know a thigh, yeah? It hits the batsman on his thigh, and the ball is stopped in 0.2 seconds. What was the momentum of the ball, and what was the force that the batsman experienced from this ball?
The learners now have to apply their observations to a theoretical problem. The educator works through the learners' answers with them, giving guidance when necessary.
0, is it? So the change in momentum will be from that to what? To 0, okay? That's one thing that you must understand here, okay? There will be a change in momentum. So what did you get for the force there? 32 newtons. Or I could have done it this way, where my F, this is my F, my T is 0.2, and I could have equated. What is the change in momentum? The momentum has changed from this to 0, isn't it? Okay, so I can say change in momentum will be final momentum minus initial momentum. My initial momentum was 6.4, and this will give me what? Minus 6.4, and then I'll have 0.2. And if I work these things out, what shall I get? I'll get mine F will be equal to minus 6,4 divided by 0.2, okay? And this becomes minus 32 newtons. Involve them and let them participate, let them experience these things, and, try to apply some thought-provoking, exercises where learners can do things, experience, and then they can think of ways out.
Hello, viewers at home. We have just watched a lesson on physics, and we'd like to talk about this lesson. At the studio today, we have Mike.
Hi, Tembi.
Dale.
Hi, Tembi.
And Andrew.
Hi, Tembi.
Let us talk about the lesson that we have just observed. We saw a very enthusiastic and dramatic teacher. What's your feeling about the teacher, and how does this impact on the learners?
Well, he himself talked about acting out. And I suppose it is true up to a point that we as teachers are actors. And the classroom is our stage, and the learners are our participating audience. I think one's got to be sometimes a little bit careful about carrying it a little too far. He was enthusiastic, perhaps to the point of being perhaps a little intimidating. But that can be a good thing, that can be a bad thing. I think some learners would react very well to him, but some might be almost, I suppose the word might be frightened of him. And that perhaps is not such a good thing. But he certainly has an interesting style, and no doubt about it, yes.
Don't you think he was doing it because it's a large class and he wanted everybody to be attentive?
I think it was very effective with the large class, yes. Yes, you can't not notice him in the classroom. And his enthusiasm is contagious, it's catching. And he used humor well as well.
Yeah, I was just going to say as well about the point on humor that, it would be nice to see more humor in our classes, because I think, we all learn in different ways, but humor is one of those elements. It's very forceful in establishing concepts. If somebody, sometimes the only thing people remember are the jokes and so on. And if you can turn that around and have in your humor a principle, then it really goes a long way to inculcate what we're trying to get them to learn. So I think, yes, the stylistics are good. The humor was great as well. But I think, also in our country, I think there's been a tradition of people saying that, well, outcomes-based education means that there's no teaching that happens, that the learners learn all by themselves. I think that is actually a terrible misconception on the part of some people. What it means is that there must be some way where the teacher engages and teaches at some point or you know, that this could be revision. I don't know if he was doing revising. It probably looked like he was revising also some stuff that they've done. So I think it's a good thing. But then again, one needs to balance that up with the fact that the learners need to get involved at some stage.
One of the things that he did was actually to allow the learners to play a tennis ball in the classroom. And what value does this bring in the teaching of this topic?
It certainly got the attention of the class, especially when the ball was going faster and faster. And it also provided some humour in its own way. When he then asked the question about the size of the force that they'd had to exert to stop the ball, the learners could really speak from experience. And I think also having learners there, the other learners in the class, imagine how they could have been there. It's easier for them to put themselves in that situation when they've seen their peers doing it.
He also brought in some very interesting characters that are very familiar to learners, like Makayandini and the cricket ball. What do you think about those type of examples in the classroom?
Well, it really brings the subject alive, because perhaps not all those learners would have TV, but at least some of them would have seen a batsman being sort of really knocked over by a fast bowler, and the figures he used were fairly realistic. I think he used 40 meters per second, which is 160 kilometers per hour, which is the sort of ideal, well, the sort of speed that every fast bowler would like to attain. And so yes, the calculation was really brought to life. And you know, getting back to the tennis ball situation, with the tennis ball being thrown faster and faster and faster, you know, he emphasized the mass and the velocity. So in fact, with the humorous demonstration, there was a connection between the humor and the physics.
So did you think the learner picked up the physics more than the humor that was in the teaching?
Well, I think they realized that a greater and greater stopping force is required as the velocity increases. So the force is connected to the amount of momentum which is destroyed, so to speak, as they catch the ball. So I think there's a direct connection between the humorous instance and the physics.
I think he could have been a little clearer, though, in terms of, in the first demonstration it was speed that was different, and in the second demonstration it was mass that was different. And both of those quantities together make up momentum. And therefore, in the first case the fast ball had more momentum, in the second case the heavy ball had more momentum, and in both cases a bigger force was required. So I think it was a lovely demonstration, but I think he could have brought the physics out a little bit more strongly.
Thanks, Dylan. What do you think about his questioning style?
Yeah, Timmy, I think he used that very well, again, to make that connection between the everyday experience and the physics itself, to develop. We're talking about conceptual development. He's developing the concept of momentum and so on. And so he's using humor, and what he's doing is using a humor, or is using you know, something like cricket, which is something which is out there. So he's bringing their day-to-day experiences or things they see on the TV into the classroom to make it relevant. But what he's doing in a very clear way is making the connection so that whatever he brings in actually reinforces the physics which he's trying to get across. And he uses questioning as his tool to do that. So I think his tool was, for lack of a better word, very artistically used to make the connection.
Okay, and what do you think about some of these words not being finished, like velo, and then the learners would say city? As he was asking those questions, he had to ask the learners just to finish the latter part of the question. And I think maybe he should try to avoid that sort of thing where he answers the question himself and chorus the question with the learners.
Yes. Sometimes he was conducting a bit of a choir there.
And what do you think about the main things that the learners benefited from this lesson?
I think they got a real feel for what momentum is, because momentum is quite an abstract concept. Learners have an idea of what mass is, they understand what velocity is. But when you get to momentum, they don't have such a good feel for it. For example, they'll battle to write down the unit of it correctly, whereas they don't have that problem writing down the unit for mass or the unit for velocity. And it is more abstract. And I think by giving them something very concrete, he gave them a better feel for what momentum really is.
Anything else?
I think what he did very well, even just as Dale has mentioned, that we went from the concrete to the abstract, which is brilliant, you know, the throwing of the ball. I mean, these are real experiences. He's trying to get across a very difficult concept, an abstract concept, but he's taking it from the concrete, you know, things they can feel, things they are familiar with, Makayantini, cricket and those kind of things, so they can make the association. He goes into the abstract, and once he's there, he also then moves on to get them to solve a problem, which I think is excellent, because now what he's doing, he's saying, here's a real situation, you know, can you use the formula to solve the problem, which is developing their problem-solving skills and ability to take the concept itself and apply it in different situations, which is a higher order form of actually demonstrating that one has grasped the concept. So I think those are the sort of things that they've learned, basically ability to solve problems, using concepts, to draw on concepts in order to solve a problem, which is a very important skill.
It's not only a science lesson, it's a language lesson, it's a social interaction lesson. So there are a wide variety of different interpersonal and social skills being learnt there, and being very well managed by the teachers. Obviously got very, very good control of the classroom situation.
I haven't seen the use of the textbook. Do textbooks still have a value in the teaching of physics?
Absolutely, but not in the traditional way where the teacher might read from the textbook and follow the textbook rigorously, but I think they're an important resource in the classroom. There is a resource of problems for learners to work through, and they're also a resource for learners to kind of reinforce their own knowledge, and then they can also be used in quite interesting exercises, getting learners to interact with the text in different ways. Instead of just reading it, to perhaps have to give a heading to each paragraph, or to identify the key word in each paragraph, or whatever. But there are a variety of ways that one can interact with the text that helps one to really get to grips with the content of the text.
I think that perhaps we could have also used the textbook in the group work, you know, to use the textbook as a sort of reference point, and to say to learners, you know, in your discussions, you know, can you also use the textbook to assist you to solve the problem? I mean, one is not saying that, you know, this must be done in all situations, you know. Teachers need to realize that the variety is the spice of life when it comes to the classroom situation. But definitely the textbook is a fantastic tool which should be used and could be used more in group work, I think anyway.
Are there any other issues that you'd like to raise that came from the video?
Again, just a small point is that he used the sporting examples to illustrate some principles in physics. And you know, you can go the other way around. There's a lot of applications of science in modern sport. Perhaps he could have talked about that. And that's just something for people to think about anyway.
Anything else?
A very little thing. I thought it was good that in giving that problem, the Makayantini problem, that he just made sure that everybody knew what a thigh was, so that people don't get stuck on what's actually an unimportant word in the question.
I think that's all we have for today. Thank you, Mike. Thank you, Dave.
Thank you,
and thank you, Andrew. Thank you, viewers at home. I think you enjoyed the lesson, and we'll see you next time. Bye-bye.